Hello everyone. We'll start uh, today's lecture of image and speech processing by talking about image transformations and what are the image transformation techniques that we are going to deal with. Right? So today's topic will be the image transformation techniques. It is the continuation of our previous video lecture. Right? In our previous video lecture, we have dealt with if U is a set of samples. U is a set of samples in spatial domain. Spatial domain. Then the frequency domain. Frequency domain. Frequency domain representation of the same vector U can be obtained by multiplying the vector u with the unitary matrix A. So here u is defined as the input, A is the coefficient matrix or the unitary matrix. B will be our output function. Right? So we talked about what is unitary matrix, we talked about how u should be and what will be my output function. Right? So in our image processing, we are considering discrete signals. So u is a set of discrete samples. Since it is discrete, we are considering n number of samples represented by u is equal to u of n 0, which is ranging from n minus 1, where n is ranging between n minus 1. So we'll have n number of samples. Since u is a vector, we are considering a 1D function. 1D function, the size of u will be, size of u is equal to n cross 1. So if we are considering the transform vector, v, we can write it as v is equal to a into u, where a is the unitary matrix, u is the input vector, v is the transformed vector. Very similar to what we have discussed previously. So if u is of size n cross 1, then a is of size n cross n, which results in v being size of n cross 1. So when we talk about in terms of sizes, u is a set of n samples. So the matrix is of n cross 1. A is a unitary matrix, which is also called as coefficient matrix. So we get our transformed vector as v equal to n cross 1. Right? So similarly, now we have v equal to au. So if we convert this matrix representation into mathematical representation, we can write vk is equal to sigma of a k. So we can write our matrix v as v of k equal to sigma, which is ranging from n equal to 0 to n minus 1 summation ak of n u n, where k is ranging from 0, 1 to n minus 1. So if this is a 1D representation, so if we want to write the 2D representation of our signal v k comma l, we can write it in the form as v k comma l double summation, where k is ranging from n minus 1, l is ranging from 0 to n minus 1, akl, where So the 2D function can be written as v of k by k of l double summation k equal to 0 to n minus 1 sigma l equal to n minus 1 akl m of n u m n, where k and l are ranging from 0 to n minus 1. Right? So we have this function which we can write it as v equal to au. Right? Now, if I want to if I want to get back my u matrix, u vector from my above equation, then I can write it as A inverse of V equal to A inverse of A into U, which is equal to I into U. So I can write my unit vector or my input unit vector. I have obtained it from A inverse of V. Since A is a unitary matrix, I can write A inverse equal to transpose of my conjugate. So I can get A is equal to A transpose of V. Right? So if I write it in mathematical form, I can write U of m comma n is equal to double summation of k equal to 0 to n minus 1, l equal to 0 to n minus 1, a k l m n, which is the conjugate, into v of k comma l. So from this we can know that v is the basis function, A is the unitary matrix. So my input image, I can represent in the form of basis function as well as unitary matrix. Based on our coefficient matrix or the unitary matrix or the coefficient matrix, or in other terms we call it as kernel. Based on that, we can define the image transformations as orthogonal and non-sinusoidal. Or the other name for orthogonal is sinusoidal and non-sinusoidal. So the coefficients are obtained from sinusoidal equations or non-sinusoidal signals. When we come to sinusoidal orthogonal signals, the basis functions are sinusoidal in nature, and then examples of them are Fourier transform and discrete Fourier transform. When we go for non-sinusoidal signals, the basis functions are non-sinusoidal in nature, and the examples of them are Haar, Wash, Hadamard, KL, and slant. So the non-sinusoidal signals are also orthogonal to each other, but the basis functions are non-sinusoidal in nature. But whereas we come for orthogonal or the sinusoidal the basis functions are sinusoidal in nature as well as they are orthogonal in nature. So when we talk about the orthogonal signals, orthogonal transform. The first one that we want to talk about is the Fourier transform. First one is the Fourier transform. So if I say f of u, let's consider the 1D representation of the Fourier transform. So if f of x is my input, then my Fourier transform of f is equal to represented as f of u, which is given by integration minus infinity to infinity f of x into cos 2 pi u minus j 2 pi ux of dx. Right? So if my Fourier transform of my input is given by f of u is equal to minus infinity to infinity f of x into cos of 2 pi ux minus j 2 pi ux into dx, which can be concisely written as minus infinity to infinity f of x into e power minus j 2 pi ux dx. So this can be written in the form of e power minus j 2 pi x. Right? Now, if I want to talk about my inverse, if I want to talk about my inverse Fourier transform, if I want to talk about my inverse Fourier transform, from that means from u of u, I am getting my f of x back. So my I have done f of x to f of u by using Fourier transform. Then I am doing my inverse Fourier transform on f of u to get back my f of x. So f of t and inverse Fourier transform equations are called as the transform pairs. So this is our transform pair. So if I want to get back my inverse Fourier transform, if I want to get back my f of x from f of u, then I can write it as f of x is equal to integration minus infinity to infinity f of u into e power minus j 2 pi ux dx. So instead of minus here, I have a plus in my inverse Fourier transform, right? So this is the 1D equation for my inverse Fourier transform. This is my equation for 1D Fourier transform. This is my 1D inverse Fourier transform. This is my 1D Fourier transform. If I want to convert this into a 2D function, then how do I do it? So I will slightly modify this equation by f of u comma v is equal to f of x comma y into cos of 2 pi u x minus j sine of 2 pi u x into cos of 2 pi v minus j sine 2 pi v into 2. So concisely I can write it as e power 2 pi ux plus 2 pi vx dx. So f of u comma v, which is this is the 2D transform function. When we come for inverse Fourier transform, we can write it as f of x comma y, which is our input, we are obtaining from our transform function, where f of e power plus j 2 pi vy of dx. So this is now 2D transform function. So our 1D transform pairs and 2D transform can be obtained from the exponential functions, which is given by the integration, which is the double integration. F of u comma v is the double integration of minus infinity to infinity f of x into f of x comma y into e power minus j into 2 power ux plus 2 power vx dx. So when we talk about our inverse transform, it is double integration minus infinity to infinity f of u comma v into e power j 2 pi ux plus 2 pi vy dx. Right? So now, since we are talking about our discrete images, we can term the Fourier transform as discrete Fourier transform. So we can, instead of the double integration for calculating our Fourier transform as well as my inverse Fourier transform, I will replace them by using double summation, where k is equal to 0 to n minus 1, L equal to 0 to n minus 1 for n for n samples. So when I am considering my discrete image, I am considering my Fourier transform is all called as my discrete Fourier transform, and this discrete Fourier transform is calculated for n number of samples. It's calculated for n number of samples. So my integration, my double integration, which I am doing it for minus infinity to infinity, I am converting into summations where it is ranging from 0 to n minus 1. So my other orthogonal transformation technique is the discrete cosine transform. My other transformation technique apart from Fourier transform, which is other time called as discrete Fourier transform, is DCT, which is discrete cosine transform, cosine transform, where my coefficient matrix A, K, L, M, N in two-dimensional is given by alpha of n into cos KL plus 1 by n by 2n into cos 2n plus 1 by n by 2 capital N. Right? So if my coefficient matrix is given by alpha of m into alpha of n, where cos of 2x plus 1 pi m by 2n into cos of 2l plus 1 pi m by 2n, this is called as DCT, which is discrete cosine transform, where alpha of m equal to alpha of n equal to 1 by root n if m equal to n equal to 0, if otherwise square root of 2 by n for otherwise, for rest all the cases, right, where m n values are ranging from 0 1 to 2 so on n minus 1, 0 1 to so on n minus 1, right. So this is my coefficient matrix for my discrete Fourier transform. Now if I consider my transform function f of u comma v, then I can write it as double summation k equal to 0 to write it as k equal to 0 to n minus 1, L equal to 0 n minus 1, where f of x comma y into alpha of m into alpha of n into cos of 2x plus 1 pi m by 2n into cos of 2l plus 1 pi n by 2n. If I want to calculate my inverse DCT transform technique, then from where I can get back my f of x comma y, then I write it as f of k equal to 0 to x equal to 0 to n minus 1 sigma y is ranging from 0 to n minus 1 f of u comma v into alpha of m into alpha of n cos 2k plus 1 pi m by 2n cos 2l plus 1 pi n by 2n. So from this we can see that our inverse DCT function and our DCT function are same. which is given by the formula alpha of m into alpha of n cos 2x plus pi m by 2n cos 2l plus pi n by 2n, where m and n ranging from n minus 1. So this is our coefficient matrix. This can also be called as our kernel. Right? So alpha of m equal to alpha of n is equal to 1 by square root of n, where m is equal to n equal to 0 and square root of value is square root of 2 by n for all other cases. Say suppose m equal to 1, n equal to 1. For all these cases, the value of alpha is equal to square root of 2 by n. So when we try to calculate our coefficient matrix, we get the basis functions, the discrete cosine basis functions images as shown here. So this is given by the basis function, which is KLM00, KLM01, so on and so forth. These are the coefficient matrices by which we multiply our input image U and we get our output image V. So the next transformation technique that we are going to talk about is the Walsh transform. So if we consider this is a non-sinusoidal signal, non-sinusoidal transform technique. This is a non-sinusoidal transform technique. So if I'm considering a 2D function, then my Walsh transform, I can write it as transform kernel. My Walsh transform kernel, I can write it as, which is given by mn is equal to 1 by n into pi of I equal to 0 to n minus 1 into minus 1 power bi of x into bn minus 1 by I of u plus bi of y into bn minus 1 by I of v. So in simpler terms, I can write it as 1 by n into pi of I is ranging from 0 to n minus 1 minus n power m t, say suppose t, where t is equal to bi of x into bi of n minus 1 by I of u plus bi of y plus n minus 1 minus y of v. So this is my Walsh transform coefficient or my kernel. This is my Walsh transform coefficient kernel. So this, where here my bi of x is the bit representation of x. If we consider the bit representation, then this is the ith bit representation of x. Example, if we consider x equal to 2, okay, and the number of bits by which x is represented is 4. Say this is just for an example. Say then n is equal to 4. Here whatever n we are considering here is given by the number of bits by which x is being represented. So here we are considering n. So n as 4. So x can be represented, which is 2, can be represented by 4 bits as 0, 0, 1, 0. So which implies that my 0th bit of my value x is equal to 0. My first bit value, my first bit value of my x is equal to 1. Then my second bit value of my x is given by 0. My third bit value of my x is given by 0. So similarly, if x equal to 5, then my representation would be 0, 1, 0, 1. Then this is my b of 0, this is my b of 1, this is my b of 2, this is my b of 3. So here, if we observe that the Walsh transform is dependent upon the bit representations and the number of bits that are being used. So this is why we call it as non-sinusoidal transform technique. So if this is my coefficient matrix, then my transformation kernel, is wxy, then my then my transformed vector, transformed image f can be written as double summation where k is equal to 0 to n minus 1, l equal to 0 to n minus 1, f of x comma y into wklmn, which is given by this equation. So my Walsh transformed of my image would be given by this equation. This is my Walsh transformed image. If I talk about my inverse Walsh transformed, then I can get back as f of x comma y, which is equal to double summation of x equal to 0 to n minus 1, y equal to 0 to n minus 1, f of u comma v into Walsh k m n. So if we observe that for Walsh transform also, my forward kernel as well as my inverse kernel, they both are same. So if we come up to our next non-sinusoidal transform technique is the Hadamard transform. The kernel of Walsh-Hadamard transform is very similar to the Walsh-Hadamard by simply changing a single bit. So I can say it by 1 by my coefficient matrix or my kernel of my Hadamard transform. I get it by 1 by n into phi of I equal to 0 to n minus 1 into 1 power t1. So I represent it by t1, where t1 is equal to bi of x into bi of u plus bi of y into bi of v. In our Walsh transform, the same equation was given by bi of x into bi of n minus 1 minus I of u plus bi of y into bi n minus 1 minus y of v. So instead of I'm considering this I. So this is the Hadamard transform function, coefficient matrix. This is my Hadamard transform function. This is also called as my Hadamard kernel. So my forward kernel, my forward kernel is given by this forward kernel, and my reverse kernel is same as the forward forward kernel. So we observe that for DCT, Walsh and Hadamard, the forward kernels and the reverse kernels are same. But we come for discrete Fourier transform or the Fourier transform, they are differing by a sign, right? So for forward kernel, we have it as e power minus j 2 pi ux plus 2 pi vx vy of 2n, and our reverse kernel is given by e power j 2 pi ux plus 2 pi vy by 2n. So this is our for discrete DCT, Walsh and Hadamard. The forward and the reverse kernels are same. For Fourier transform and the discrete Fourier transform, they are represented by exponentials which are differing by a sign, positive and negative sign. So this is our Hadamard transform. Let's do one problem. Let's calculate Hadamard coefficient matrix of size 2 cross 2, right? So Hadamard transform coefficient or my coefficient matrix is of size 2 cross 2, which implies that our image is also of size 2 cross 2, right? Now say suppose my each and every bit is represented. Say suppose n is given as 4. So what are my possible functions? n minus 1 minus 1 of t, where t is equal to bi of x into bi n minus 1 minus y of u plus bi of y into bi n minus 1 minus y of v. So we have our kernel as given here. So this is our Hadamard equation. This is our Hadamard transform function. So if we observe here, we can say that this Hadamard transform is a separable transform function. How? We can say that KLMN is equal to 1 by square root of n pi of 0 to n minus 1 power bi of x into bi of u into 1 by square root of n into pi of I equal to 0 to n minus 1 of minus 1 b1 of y into bi of v. So if we observe that our 2D function, the 2D Hadamard transform function can be written as a combination of two 1D functions. So this technique of converting my 2D transform technique as multiplication of two 1D transform functions, this we call it as separability in transforms. So we observe that my Hadamard transform I can convert into two 1D functions. So this I can represent it as WKL of m into WK WL of n. So we even observe that these two functions, two 1D functions are same. So they can also call it as the symmetric transform functions. So from this example, we have observed that our Hadamard transform is separable, symmetric, as well as it is a unitary matrix. Unitary matrix means A inverse equal to A star conjugate of my transpose, right? So my Hadamard transform is separable, symmetric, as well as unitary matrix. So this is the very important parameter for transform matrix or the transformation techniques. So we can observe that Wk of m into Wl of n. So from this we can conclude that if we calculate my Wk of m, it is very similar to my Wn of n, right? So from this equation we can calculate our, from this we will calculate our Wk of m for my proposed example. So it is 2 cross 2. So my x values range from 0, 1. So my x values range from 0 and y, whereas my y values, my k values range from 0, 1, whereas my m values range from 0 and 1. So my what are my combinations of k and m? I can get 0, 0, 0, 1, 1, 0, 1, 1. So I can see that my Wk of m is a 2 by 2 matrix, and the coefficients are 0, 0, 0, 1, 1, 0, 1, 1 can be obtained from my above equation. So consider now I want to calculate W0 of 0. So which implies that k is equal to 0 and m equal to 0. We have given that n is equal to 5, which implies that k is represented by 4 bits. So 0, 0, 0, m is given by 0, 0, 0, 0. So m is equal to 0, 0. If I want to calculate my coefficient matrices, then I can say that W0 of 0 equal to 1 by square root of n square root of 2 into phi of I equal to 0 to 3 minus 1 bi of x into bi of I into u. So here x equal to 0, u equal to 0, which can be written as 1 by square root pi of, which can be written as minus 1 power bi of 0 into bi of 0 of u, which is 0 into minus power bi of 1 of 0 into bi of 1 of 0 into minus 1 power bi of 0, bi of 2 of 0 into bi of 0 into minus 1 power bi of 3 of 0 into b3 of 0. So which will turn up to be minus 0 into minus 1 0 minus 1 0 into minus 1 0, which will turn up to be minus 1 by square root of 2, right? Now similarly, if I want to calculate for W0 of 1, I get as k equal to 0, m equal to 1. So for n equal to 4, k can be written as 0, 0, 0, 0, m is given as 0, 0, 0, 1. So my Hadamard equation I can calculate here as, which is very similar. So on and so forth. If I calculate my Hadamard for my Hadamard for my 2 cross 2. Hadamard cross my 2 cross 2. I get my equation as 1 by square root of 2 into 1, 1, 1 minus 1. So this will be my coefficients of my Hadamard transform function. So using this equation, and if I can multiply it with my unit image u, and I can get my transform image v by multiplying this function. So we have observed that Hadamard transform is separable, symmetric as well as unitary. Since it is separable and symmetric, we can calculate our coefficient matrices by combination k and m, which turn up to be 4 combinations 0, 0, 0, 1, 1, 0, 1, 1, from where we observe that our separable 1D transform function is of size 2 cross 2. So we can even say that my WL of n is also matrix of size 2 cross 2. So my end matrix or my transform vector will also be of size 2 cross 2. So I get my transform coefficient matrix for a cross of size 2 cross 2 as for any image as 1 by square root of 2, 1, 1, 1 minus 1. So this is the reference that we have been talking about. This From this we can get to know all about our image transformation techniques.
Like, share and subscribe. Hit the bell icon for more updates.